Hello, hello.
Okay, I will start because I think then Vaibhav gets the time full. Okay, so it's a pleasure to welcome all of you back to Colloquium after missing 1 week. So today we have a special colloquium, of course, because not special in terms of it's a normal colloquium, but special because made possible because of Vaibhav, who is a colleague of ours in the institute. And it gives me pleasure to introduce Vaibhav. Actually, Vaibhav did his bachelor's in physics from University of Mumbai. He's a localite in all the word, in the sense of the word. And then he did his master's in physics from IIT Bombay. And this was from 1998 to 2000. And this was a special time because in 1999, Vaibhav and I crossed paths because we both were VSRP students in the institute. And I have very fond memories of those times. But somehow, at least for my side, I lost track of where he was. But it seems at that time, VSRP program had this very special opportunity that if you were to give an interview, you would be directly selected. If you're a top VSRP student, you will directly get selected to the PhD program. And Vaibhav was one of them who actually continued in the institute in Department of Nuclear and Atomic Physics with Professor E. Krishna Kumar. He did his PhD with EK, and this was on free and Rydberg electron attachment to molecules. So this was from 2000 to 2006. And then from 2006 and so on, he continued as a visiting fellow first. And then for a short time, he visited Sadiq's lab when Sadiq was, I think, just also starting up and in Raman Research Institute. And then went to Yaron Silberberg at the Weizmann Institute to do his postdoc. After finishing his postdoc in close to 2009, I think.
2010.
2010, okay. He came back and joined the institute as a visiting fellow, as a faculty, and then has been there ever since. And the fun part is that I also joined the institute very similar in time. And the most interesting thing about Vaibhav is I could not recognize the man. And what has happened over the time was Vaibhav had hair. And he was not this, maturely built. So he actually, when I first saw him, I was kind of perplexed whether I know him. And he told me yes. and then we reconnected again. And we have been very close ever since. And so I'm very happy that Vaibhav is giving this colloquium. Unfortunately, I'm sorry. I apologize that the colloquium had to be postponed, but thank you that you're here and you're going to hear your wonderful science. And today is on low energy electron molecule collision. Do we understand it fully? Vaibhav?
Yeah. Hello. Yeah. So thanks, JD, for that elaborate introduction. And yeah, it's always pleasure to talk in TIFR and connect with colleagues. So today I'm going to talk about low energy free electron molecule collision. And what I'm going to do is, as you can see, electrons are discovered more than 100 years ago. And electron molecule collision is a very, very old field which has seen many, many years of progress. So giving a detailed review of this field in one colloquium, including my work, is not going to be possible. So what I'm going to do is, I'm not going to go through all the progress that has happened over the years in this field, but I'm going to just touch upon a couple of important milestones that are there in this particular field and why this is still interesting field and still people are finding it very intriguing to get new results. Okay, so first thing first, I'll click on that. Yeah. So first thing first, acknowledgement to all the people who are associated with my group right now, but more importantly, Suasis, who is now at Ganil, and Akshay, whose work is predominantly presented today as the talk progresses. This is a very interesting experimental slide, and it is from 1922. This was the first sort of an apparatus where in vacuum, people, in this particular apparatus was used to measure electron impact ionization of mercury. Okay, and that was a time when, you know, the electrons were used to probe atoms and molecules, and the Bohr model has come just a decade ago. So people were trying to look at all sorts of properties of atoms and molecules, and electrons were used to probe it. So this is an interesting apparatus because this is an apparatus which was eventually also used to detect negative ions for the first time, and we will come to that. So when electron interacts with molecule, it actually can do many things, right? So these interactions we can broadly divide into two types. One is elastic scattering, where you know, the incoming electron just goes out with the same kinetic energy, but may not be the same, same momentum. Okay, so this is the most common channel that is present at all energies. But along with that, you can also have inelastic scattering, and inelastic scattering has a plethora of processes that can take place. And I will not bore you going through each and every step of it. However, if you look at it carefully, there are only one or two places where the electron actually get attached to the molecule and forms a negative ion. So electron being a negatively charged particle and an atom or molecule being a neutral, the expected reaction is that electron will knock out another electron or will excite the molecular atom. But sometimes it can also attach to molecule and form a negative ion. And when this negative ion is formed, you can have this negative ion decaying in various ways. One of the ways is dissociation, and we will look into that because that is something that gives you real information about electron molecule interaction at the molecular and the molecular properties subsequently that come into picture. Now, I'm going back to the history. The same apparatus was used in 1930, and so this is a very funny paper because Lozier, it's a one-page paper, and Lozier says that they just happened to look at negative charge and they found out something which peaks at certain energy. So they were looking at electron impact ionization of water, and just to calibrate it for the masses, they put in hydrogen. And I mean, of course, I'm sure that the potentials must be connected opposite by mistake because I don't see why they were looking for negative ion, because that was a time the H minus was something which was not very well established. Yes. Huh? No. Yeah. So, I mean, this was a time when the stability of H minus was established and people were looking at H minus. So that might be the case that they were genuinely looking for H minus. However, electron impact processes giving negative ions were not yet brought into picture by neither theorists nor experimentalists. So this is the first experimental evidence where people found out that when they collide electron with water molecule, they get H minus, and they collide H2 also with water molecule, they do get H minus. And this is the first paper where they actually talk about negative ion formation and observation of that. And then the paper goes on talking about thresholds and electron affinities and all sorts of measurements. And this actually opened up a series of experiments where people now started looking at electron collision with molecules and looking at various channels of negative ion formation and using that to study the properties of the molecule. And the time passed and a lot of theoretical model came up. The problem with negative ion is that neutral being neutral has no effective charge. The electron attachment becomes very, very non-trivial. Okay, so the interaction has to be a long-range interaction. At the same time, it has to also be weakly bound, because the electron is going to polarize the molecule and then going to get trapped in that polarization potential. Now, as a result, having a theoretical model for negative ions is not something which is trivial. People are still working hard on it. And why I'm flashing this particular paper is because this is the paper which uses the R matrix method, which is a very well-known method in scattering or charge particle scattering community, where you can say that around a target molecule, you build a sphere. Outside the sphere, you do physics. Inside the sphere, you do chemistry. And then you say that on the boundary, the physics and chemistry matches. Okay, so that's a nutshell of R matrix calculation. And this is a paper which actually claims that they have sorted out all the negative ion related problems. This is a paper which actually gave a genesis of something called UK matrix code, which is now rampantly used by many people in electron collision community, as well as people who are looking at electron collisions to applications like astrochemistry, applications like plasma physics, applications like radiation damage. They use this code to find out various kinds of information, like what are the excited states of negative ion, what are their energies, what are the cross sections of these processes, etc. So that in that sense, this is a milestone in this particular field. And then after this, so inside the sphere, you have a molecular ion, and then it has been treated with a quantum chemical, various quantum chemical strategies, right? So you have many. So quantum chemistry has developed. I mean, that quantum chemistry is a huge field which has developed for neutrals and positive ions. And then there is the scattering community which talks about the scattering in the physics sense from the charge particle collision. And dealing with these negative ions with the absorption potential, people have now developed quantum chemistry based picture to describe these intrinsic properties of these negative ions. So that's why it is chemistry. Okay. So now, so this tells us that we have theoretical model. Now you tell us a molecule and I'll tell you everything about it. What kind of resonances, what kind of excited states, what kind of cross sections. And when that happens, people say field is dead. Okay, because now everything is known, things are fine. Okay. Now, then came a classic paper in 2000. This was a science published by Luosan. And this told people that low energy electrons, what people thought about is not necessarily only, academic matter where it matters, but the low energy electrons play a very important role in DNA damage, particularly in radiation damage. So what happens is that if you have a high energy radiations, charged particle or light, like gamma radiation, when it interacts with matter, it generates several electrons, and these electrons can undergo multiple collisions, thermalize, and they can generate a lot of low energy electron particles. And these low energy electrons can go and attach to DNA if they are formed in the cell. And this DNA can undergo single and double strand break, which can eventually either kill the cell or can cause cancer. Okay, so either way it can go. And this particular paper again rejuvenated the field, because now people started looking at chemistry from electron collision point of view, and that's where actually before this, the electron collision was looked into from purely plasma physics and plasma chemistry point of view, but this is the place where it started making it interesting for biologists and radiation chemists. And that's where a lot of organic molecules have been started, looked into. And then the field flourished. So there was a big spurt of experiments that went on around the world. And then, of course, there was a R matrix code, which was already there, which was, telling everything about what's going on. And so there was a series of work that went on in the early 2000s, where there was experimental measurements of absolute cross sections, and then you compare it with the theoretical values that are coming out of R matrix code, and everything seemed to be going on fine. Yes.
for all sorts of.
Yes, yes. So that particular paper talks about H2,
Right.
which is the simplest. But now they have developed it so much that now bigger molecules, not proteins,
Okay.
but relatively bigger organic molecules can be handled.
And that's important for all sorts of application, medical and.
Yeah. In principle, yes. So as I said, low energy electrons, they are generated by the radiation interacting with material and all that low energy. So when I say low energy, typically less than 25 eV. And what you have is you have all sorts of processes that can cause damages to the molecule. And they are important from now plethora of processes that use these interactions or have this interaction by default, like radiation chemistry, astrochemistry, radiation biology, material science, environmental science, the atmospheric science, and so on and so forth. Now, why is it so important or difficult to handle these negative ions theoretically? And the problem is following. If you look at a simple picture, I have a neutral molecule. And if I'm going to attach an electron to this neutral molecule, I'm always going to climb up in energy than this neutral molecule. Now, depending on the electron affinity of this molecule, the negative ion ground state can be below or above this. Now, if it is below it, then it can have several excited states, but eventually it is going to ionize, and that ionization potential has to match with the position of this neutral. So that means every time I'm going to attach an electron to a molecule, I'm going to a state which is lying in a continuum of this negative ion. And any state which is lying in a continuum is a nightmare for theoreticians to handle. That is because you have to now look into the coupling with the continuum, and taking into account this particular aspect in calculating the excited states, their properties, their dynamics is a very, very difficult task. Yes.
Just a very naive question. So why is it not a bound state?
Why
is it not a bound state and a continuum of states?
It is a bound state. The only thing is that its energy, if you look at its energy is above the neutral because you are attaching with a positive energy electron, and the neutral is the ionization of negative ion. So it is always above this neutral energy. So it is always going to match with a neutral plus free electron. And that's why it's a bound state in continuum and hence a resonance. Okay, good. Now these states are studied by photoelectron spectroscopy of negative ion as well as electron collision. That's what we do in our group. Okay, so then what is so special about these negative ions? So there are many ways by which these negative ions can be formed. And the way in which the negative ion forms tells us about the property of the molecule, okay, in a sense. So for example, the simplest way of forming a negative ion is something called single particle or shape resonance. And what happens is that the incoming particle actually interacts with molecule, polarizes it. So now you have a polarization, induced polarization, which is causing an attractive potential. And then you have a centrifugal barrier because of the free electron. And this opposing potentials will give you a barrier, effective barrier, and this barrier can trap an electron. Okay. So this trapping happens because of the shape of the potential between electron and molecule, and that's why it is called shape resonance. Okay. Again, it's a positive energy, so it eventually will decay by either tunneling or usually tunneling, or if it is slightly above, then just over the barrier. Okay. Now this decay tells us that the negative ion resonance is short-lived. Okay. Now, this is one way, but if the electron comes with sufficient energy, it can actually excite the molecule. Now, that's why electron collision with molecule is interesting, because it gives you a handle or understanding of electron-electron correlation, which is a very long-standing problem in for quantum chemists as well as for atomic and molecular physicists to understand how does the electron-electron correlation been handled or are present, and what role does it play in properties of the molecule. And this is a nice example where electron which is coming in from outside is going to interact with molecule, and if it has sufficient energy, it can excite the molecule. But here, there are two possibilities. The first possibility is that the electron comes in, it dumps all its energy, the molecule is excited, and now the neutral excited state is polarized because of this charged particle sitting around with a very low energy, and the charged particle get trapped. That's the shape resonance. So it's exactly same thing that what happens with the ground state, but with the excited state. So electron has come in, it has dumped its energy and got trapped. And this kind of resonance is called two particle one hole. Obviously, because electron is excited, so there is a hole. And now you have one more particle which is coming from outside. So there are two particles in the excited state and a hole in the lower state. Okay. But there is another kind of resonance, and this is thanks to nuclear physics that the atomic physicists learn about Feshbach resonance, which were first discovered in nuclear physics, but eventually it were also adapted by atomic and molecular physicists. And here, the incoming electron does not have sufficient energy to excite the molecule, but still it dumps all its energy and gets trapped. Okay. Now imagine this particular resonance, it doesn't depend on the shape of the potential. It just gets interacted, it just interacts with multiple electrons in the system, and the electron is such that the negative ion is stabilized. Okay. Now, as a result, this is a channel that cannot decay by leaving the molecule excited. This channel has to decay by molecule going back to the ground state. And that is why it is called a closed channel. And these are the resonances that are the most long-lived resonances that people have observed. Okay. But again, because of the lifetimes and because of their widths, they are very difficult to calculate. Yeah.
Second case is all the energy dumped inside the nucleus or something.
Not nucleus, in the electron cloud. It's all in the electron cloud.
Okay.
Yeah.
The bound electron.
The bound electron.
But
yeah.
you said it's also not excited.
Correct. So the overall, okay. So the negative ion appears, if you look at the configuration of this negative ion, it appears as if it is its parent state is excited neutral, but it is not. It is still a one particle, it's still a one hole two particle resonance. But if you cannot easily just knock out the electron. If you knock out the electron, the neutral has to go back to the ground state. It cannot remain in the excited state. So if you look at the total energy of the system is not the excitation energy of molecule plus electron. The total energy of the system is less than the excitation energy of the electron of the molecule, but it is slightly less. And that slight less is you can say it's like an electron affinity of the excited state. So that takes care of lowering the overall energy. Okay, it's a little complicated entity, but we will discuss if you. Yeah.
So that state exists only as like a 3-particle emergent thing.
Yeah.
It's not okay.
Yeah. Yeah. Okay. And that's why it is long lived, because unless there is a chance of electron to leave, the system will stay. It's not tunneling that will kill it. Okay. Okay. And then of course there is another resonance, which is a very slow electron when it approaches, then it just breaks all approximation that chemists love, which is Born-Oppenheimer approximation, where nuclear motions are too slow compared to electron. But if the electron is very, very slow, then everything is, of the same time scale. And then the resonances are even worse to calculate. Okay. Yeah.
I was wondering, so the damage to DNA, etc., is a condensed phase reaction, right? I mean, mostly we're discussing right now gas phase
Yes.
type situations. So
Yes.
how does solvation, etc., actually impact this? I mean,
Yeah.
would the same processes be applicable?
Yes. So if you look at the resonance position, so what people did and what we also do is we look at the condensed phase molecules in condensed phase and look at these resonances in the form of negative ions, which are getting either generated and coming out of these entities. And when you look at the resonance positions, they match fairly well with the gas phase with a slight shift. That shift comes because of the binding of the surfaces. Okay, so there's all the solvation, etc. So, for example, in the case of DNA with the cell, the solvation, water also plays quite a lot of. I mean, the water molecules around it also play a lot of role in binding that electron. Okay, so that is still an ongoing question. Is that when the DNA strand break happens, which part of the DNA which is actually responding to this electron? That is still an open question. Okay. Okay. So now when we have this negative ion can now decay by giving away electron, which is called auto-detachment. Or it can, if it survives this auto-detachment, then it can dissociate into a negative ion and a neutral. Okay. And this decay probability is exponentially dependent on the dissociation time. Okay. This is very important. So if my dissociation time is longer, my decay probability is lower and I will have less number of ions dissociating. Now, in all our experiments, what we look at is the negative ion dissociation. This is called dissociative electron attachment. Okay. Now, this was all fine. People were finding newer molecules, looking into collisions, looking into cross section. And then in 2005, we adopted imaging technique, which is used for which was used in charge particle collision as well as in the photon collision, or photo absorption is a photo dissociation kind of experiments, to low energy electron experiments. And when we did this, now you can start. Now people could start see the dynamics of what exactly is happening to this negative ion excited state. Because so far the way in which the measurements were happening is that you are putting in electron and you look at what are the negative ions formed, and you measure the quantity, the amount of negative ion form as a function of electron energy. That's the kind of experiments which were going on. This is an experiment which actually paved the path for looking at what are the dynamics that are involved in this dissociation process. And this actually opened up a vast number of experiments all over the world, but this also started now challenging the theory, because the theory was giving us only the information about the excited state symmetry and the cross section of the process. But this is now starting posing a question, is that the kind of symmetry states that we are talking about, what are the dynamics that are stabilizing these negative ion states, and what are the dynamics which are followed by these negative ions towards dissociation. This information started coming out with these kind of experiments, which now theory has to readjust itself to address. And that's where the real Pandora's box was opened, because whatever that R matrix code was giving us was good enough to a certain extent, but was not giving the real picture of what exactly is going on. And the simplest way to look at this is to look at the simplest molecule, which is H2. And that's what we did. And today's story is all about what we have discovered in electron collision with H2, which is the simplest molecule for any physicist. Pleasure to work with, because we understand what's going on. And apparently it is nightmare for chemists to calculate, okay, for this particular negative ion state. Okay. So what does this technique do? It look at the negative ions. So you have a molecules which are randomly oriented, and now you have electron that come in, and when the electron attaches, if the dissociation process is fast enough compared to rotation, then I just measure the angle at various angle, how many negative ion fragments are arriving, and that tells me what are the orientations of these molecules which were preferred for electron attachment. Now this now leads to, if I know my initial state of the molecule, and if I know this angular distribution, then I can actually figure out what is the final state of the molecule, right? So that tells me the negative ion symmetries. But more than that, it also tells me the kinetic energy of the fragment. So that tells me the energy distribution of this negative ion excited state that is taking place. Now, when we do this, this is the form of this is the form that the angular distribution gets, and this first summation is for one resonance over all partial waves. So now, okay, so this is another concept of collision, that when you have a particle scattering, multiple angular momenta can be transferred. So the simplest way of looking at it is that you consider incoming particle as a plane wave, and when the scattering happens, different angular momentum channels will have different scattering amplitudes, and hence different angular momentum transfer probabilities. Okay, so if you now sum over all these partial waves, you will get the angular distribution for one resonance, and then you can sum over many such resonances which are present at given energy. Now for H2 being a inversion symmetric system, it's a very simple system, but it has inversion symmetry. Any process that takes place should also have inversion symmetry. And as a result, when the angular momentum transfer happens, it necessarily has to transfer either odd or even angular momenta. It cannot transfer both. So when I am exciting H2 or when I am attaching electron to H2, either even partial waves are transferred or even quanta of angular momenta are transferred or odd quanta of angular momentum are transferred, because only then the inversion symmetry of the system will be retained. Okay, so inversion symmetry tells me that. Good. And as a result, if I am transferring, for example, S state, angular distribution expected to be isotropic. If it is a P state, L equal to 1, the angular distribution is expected to be cosine square and so on and so forth. Okay, so these are the standard pictures that you expect when you measure the angular distributions. Good. Now, when we do this measurement of electron attachment to H2, what you get is following. You are starting with H2 ground state, which is the neutral state. This is the solid line. And when you attach electron, depending on the electron energy, you can access any one of these negative ion states. Okay. Now you can see at low energy, it's not a problem because there is only one state here, which is a ground state of H2 minus. Then there is one state here, which is an excited state of H2 minus. But here, there is a plethora of state that can get access. And that's where the real fun starts. Okay. And that's where the calculations become complicated. So let's see what happens. So when we measured this, you can see there are three resonances. One is at 4 eV, which is about this, the ground state of H2 minus. Then you have peak at 10 eV, which is this dissociating curve, which is a long curve in the Frank-Condon region. And then there is a sharp peak at around 14 eV, which is actually coming from one of these states from this jungle, which is giving me H minus. But now this H minus is coming out with another hydrogen in the excited state.
Can I ask a quick question? I'm sorry, I should not ask, but just a quick question. How were these potential energy surfaces calculated for all these?
No. So most of them are neutrals. Okay.
Okay.
Only couple of negative ion curves are calculated.
Calculated.
Okay. And they are old. And
so they can have changes like based on the.
They can.
Okay.
And actually they are lines, but they should not be because all of them have widths. The widths are not plotted. Okay. And that's where the real fun is. I mean, that's where the real problem for the theoreticians is. Okay. And now, as I said, we understand the three peaks that we observed in H minus. So what are we measuring? We are measuring H minus signal as a function of electron energy, and we see now three resonances. Very nice. Okay, we go to the first resonance, we look at the angular distribution, it looks like cosine square. It tells me everything is fine. Whatever theory tells me, I understand it correctly and experiment replicates it. So things are fine. Okay. Now we go to the second resonance and we see this kind of images, which are, little complicated. Don't worry about the images. The take home message from this is that look at HD. Which is the heteronuclear counterpart of H2. Now, if H2 is inversion symmetric system, does HD show inversion symmetry or not? Now, the question comes because HD being a asymmetric mass, the electron reduced mass around H and around D is different. So the center of mass and the center of charge for HD is slightly shifted. As a result, HD has a permanent dipole moment, which is not the case for any inversion symmetric system. An inversion symmetric system should never have a permanent dipole moment, but HD has. Okay. But what this tells me is that even if HD has a very small permanent dipole moment, it does not play any role in electron attachment. Because if it does play any role in electron attachment, my H minus and D minus should show difference. Okay. Because the two channels actually come from two different dissociation limits. The electron affinity of hydrogen and electron affinity of deuterium are different. So because they are identical, it tells me that the electron collision at low energy, the permanent dipole of HD does not play a role. Yeah.
They are not exactly identical.
No, they are not exactly identical because of the imaging problem on this side. So don't worry about that. You worry about this side and this side, they are identical.
Yeah, but also empirically, if you were to parameterize one as something the other plus some difference, that you can only keep putting an upper limit on that difference, and I assume at some
Correct.
point you will measure a difference, because theoretically it should exist.
So that's what we will come to now.
Oh,
Okay. So here, okay. So here actually came the first shock and the first disagreement with the R matrix calculation. And the first disagreement is following, that if you look at this, and these are the data which were already published in 1984, but people have very conveniently ignored those particular results. But our measurements also now followed them. And what it tells us, that by the analysis we can say that this resonance, which is now appearing in the 10 eV peak, it actually is a Feshbach resonance and not a shape resonance. Okay. The R matrix calculation calculates it as a shape resonance. And what we found is that right in the Frank-Condon region, it actually crosses the neutral state, neutral excited state, and it changes the character. Now, this kind of feature is very difficult to model for a theoretician, particularly for the R matrix kind of calculation. So they are saying all throughout that this is a shape resonance. What we found is that it is not a shape resonance, but it is changing its character. Now, the problem with this system is that this particular resonance has also has a very short lifetime. So it's a very broad resonance. So it's very difficult to actually demarcate whether the resonance is lying above or below, because neutral state is a very nice, well-defined curve, but the negative ion state, being a short-lived state, is a thick band. Okay, but even if it's a thick band, the R matrix calculation tell us that most of the band is above the neutral state, whereas what we are saying is that may not be the case. And so is the case with this electron scattering experiments that actually reported in 1984. So this disagreement was already there. It's just that people have ignored them. But now with these angular momentum measurements of imaging, now they are coming up in front again. Okay. Yeah. Yeah. So those are based empirical calculation based on selection rules.
Okay, but because the left side there is absolutely no agreement.
Correct. So that's what. So left side says that if you consider this calculation, okay, I'm sorry. If you consider this calculation, they are considering it to be a non-resonant process, whereas what you see is a resonant process kind of a behavior. So they are saying that the electron is not coming out as in non-resonant scattering, it is actually coming out as a resonant scattering, and that can happen only if it is a Feshbach resonance, not as a shape resonance. So that's a dissociation curve. So there is no vibrational, it's a vibrational continuum. So the broadness is much bigger than the continuum. I mean the energy gaps. These, but R matrix calculations are, that is a different. These are not R matrix. These are not R matrix. This doesn't tell about the theory, but this tells you that what is the kind of resonance it is. R matrix says it is not of that type. That's the point. But the real shocker came when we look at the angular distribution at 14 eV. And here the problem, you can see that the inversion symmetric system shows symmetry breaking. Right? And this has never been expected. And this is possible only if, instead of having a sum of, the square of the various partial waves of only one parity, if I now have the square of the sum, then I can break this symmetry. So that means I am attaching electron and I am exciting multiple quantum states of opposite parity simultaneously. This is possible because a single electron can pass on odd as well as even partial waves. Odd partial waves can catch and go to the inversion symmetric in antisymmetric system, and even partial wave will take you to the inversion symmetric system. And what is happening is that electron attachment is resulting into coherent superposition of two resonances. And as a result, you can see that the dissociation is showing interference of two quantum paths, and this interference is breaking the inversion symmetry. But now, the question is, if this is the case, what happens in HD? in principle, HD also should show this, right? Yes.
Just a little question. So if I make very, very precise measurement, can this break the coherence?
Precise measurement of what?
The coherence that you're talking about, that is of the partial waves, right?
Correct.
So if I make like angular,
So if you start
measurements-
with a electron not as a plane wave, but as emerging from a specific process in which electron comes out with a well-known quantum number, for example, an auto-ionizing electron, it will come out with a well-defined L, then you will not see this. Okay, because then it is a well-defined L. But because plane wave has all partial waves, odd and even both are allowed. Yeah.
Vaibhav, so in the previous slide, when you saw this parity, sorry, the symmetry is being broken. Can you go to the previous slide? Maybe I'm missing very simple thing. So what is the key difference between H2 and D2? Like in one case, I see it is broken and in
Yeah,
other.
Yeah,
it is
very
not.
good. Good question. So in D2, see, the only difference between H2 and D2 is that D2 is heavier. So it is going to take longer to dissociate. Now, if the two resonances have different lifetimes, then it may happen that the dissociation time change happening between H2 and D2 can change the contribution from each resonance, because one of the resonance may not survive for the D2 dissociation. That's one. Second is the dissociation time is different. So the time difference between two quantum paths also is different. So the relative phase also changes. So there are two things in interference that matter. One is the amplitude of two paths and other is the phase between the two paths. And both of them depend on time. And this time is different for D2 and H2. D2 dissociates slowly. So you have different phase as well as different amplitude. And that's why you have different contrasts of interference. Okay. Good. So what happens in HD? Now, if HD behaves like a homonuclear diatom, which is what we concluded from our previous measurement, that means the dipole moment does not play a role, then H minus and D minus should show identical forward-backward asymmetry. But if HD behaves like a heteronuclear diatom, then if H minus peaks in the backward direction, D minus should peak in the forward direction. As simple as that, right? Because now I can distinguish between H minus and D minus. I can distinguish between the two orientation. So if one orientation peaks in backward direction, the other orientation should show opposite. So when we did this measurement, we saw that they both show identical angular distribution. Identical in the sense that both of them show backward peak, not backward and forward peak. This again tells me that the permanent dipole is not playing much role in this electron capture that is happening at these energies. Okay. Something similar has already been observed in photoexcitation and photodissociation of molecule like HD, where they have looked at forward-backward asymmetry, and they have also seen that the forward-backward asymmetry identically matches for H plus and D plus. And the answer is again, at those wavelengths where they have carried out this measurement, the permanent dipole of HD does not play much role. Okay. Now, this is something which has not been done by the pictures which are or models which have been known. Okay. Now, is it something which is seen for the first time? The coherence been induced in the system, has it been seen for the first time? No. For example, in TIFR location, Dipankar has shown this, that if you collide H2 with electron, and if you look at the electron ejection from both the hydrogen atom, it actually shows a Young type interference. In the sense, now you have two sources of electron, and as a function of angle and the energy, you can see that the probability of getting or probability amplitude of getting electron from both the centers, they interfere. And as a result, as a function of electron energy as well as angle, you see the forward-backward asymmetry, and that varies as a function of electron energy, the ejected electron energy. So this is something which has been seen, but this has been seen in an electron ejection channel, not in the molecular dynamics. Okay, so that's a major difference. So has something like this, the quantum coherence, been seen in molecular dynamics? And the answer is yes. People have seen this, but not in the sense of differential cross section. They have seen it in the sense of integral cross section. In the sense, you are not breaking inversion symmetry. You are just going through the same path. It's just that you are having a S wave and D wave, and S wave and D wave interfere, And because they both belong to the same symmetry, the differential cross section will not be varied, but the integral cross section will vary. And people have shown that in electron captured by HD plus, they see this kind of oscillations as a function of electron energy. So this is something which has been seen for dissociative recombination kind of experiment, but not in electron attachment. So then the question comes, if this is happening because of multiple angular momentum transfer, is it something which has to do with the resonance, or is this a more general phenomenon which in principle should be observed for all the inelastic scattering processes? Now to explore this, we again went back to this plethora of processes and we pick up a process which is dipolar dissociation. Now what is this dipolar dissociation? So this is a very simple process. You have a molecule, electron comes in, it collides, passes on energy and goes away. And now the molecule is neutral but excited. And this excited neutral now breaks into a positive ion and a negative ion. This is called dipolar dissociation. Why this is interesting? Because then I can detect negative ion and I can use the same spectrometer to find out what's going on. Yes.
What is the dipole moment of HD in dY?
It's,
You know,
I think
less than 1.
too small. It's too small.
Okay. And okay. And when you replace H2 by HD, how much does the potential shift? Like if I were to
So the potentials, okay. So for example, the dissociation limits shift by 3 milli electron volt. Okay, but even if they shift by 3 milli electron volt, in my mass spectrometer, there are two different distinct channels because they are mass wise, they are different. So the identical dissociation limit as well as identical output, that condition is broken, which is there for interferometer, right? So that way HD should not behave, but it does behave. Okay, and we have explanation, but I will not get into that. It's more technical. Okay, so we looked into dipolar dissociation. Now, what is dipolar dissociation? So you have H2, you collide with electron. If the electron has sufficient energy, it will excite H2. Now you'll have H2 excited, and that H2 excited breaks into H plus and H minus. Okay. Okay, so this is a threshold process. Why? Because moment electron has energy more than that excitation energy, it can always give that much energy and go away. So it is dependent on energy of electron only up to threshold. Beyond threshold, for all energies of electron, this process will happen. That means it is a non-resonant process. It has nothing to do with the energy matching. Anything beyond a threshold, this process should happen. This is more technical, forget about it. So this is a non-resonant process. And more importantly, if you look at now, the dipolar dissociation threshold is 17.3 eV. And above 17.3 eV, now you have plethora of states which can give you this dissociation. So ideally, we identify two. One is this, which is going to give me very little kinetic energy of H minus. And other is this, which is going to give me a large kinetic energy of H minus. So when I do the experiment, I see two. At 20 eV, I see a blob, which is like a low energy electron H minus, which is the first step. And at higher energy, I see a blob as well as a ring. And the ring comes from the higher energy or the dissociating curve. So this is all, it's fine. But you can already see there is some problem here. The ring is showing me forward-backward asymmetry. Okay. So we do more measurement. And at various electron energies, we see different forward-backward asymmetry. This tells me that, yeah.
The center also is not symmetric.
Yeah, so the problem, I'm sorry, the problem is, the problem is when we start, these are very high energy ions. So when we start imaging these high energy ions, we have to compromise on low energy ions. So the blob which you are seeing at the center is a compromised image of low energy ions. So it has all the defects. So don't pay too much heed to it. Okay. This is a problem with the experiment. Can't help it. Okay. Yeah. So now we do see forward-backward asymmetry. We do see it depends on the electron energy. And this also means that this is the most general way I can induce a coherence in a molecular dynamics. I have an electron which is of energy beyond a threshold. It undergoes inelastic collision. And more importantly, the electron is coming from a thermionic emission. So there is no intrinsic coherence present in the electron beam. The electron beam is an incoherent electron beam, but every single electron is causing multiple angular momentum transfer, and that is something which is invoking the or inducing the coherence. And that coherence in this case is showing up in the form of forward backward asymmetry or inversion symmetry breaking. Now, this is again interesting. If this is for H2, O2 or N2 have many electrons. So this should get washed out because now you have so many such possibilities of coherent superposition, it should get washed out. But actually it doesn't. And these are the, I mean, including our group, we have seen this forward backward asymmetry in dipolar dissociation on O2. And all of us, including previous studies, blamed our experiments, saying that our experiments are bad. There might be some problem with the detector and this and that. But this is a true picture. This is actually the case. So this is for the students. If you do an experiment, if you find some spurious result, make sure that you find out that the spurious result is not brushed aside by some argument, but make sure that the spurious result is not a good science that you are ignoring. Okay. So this actually in principle could have been discovered in 1974 or 2006, but it didn't because people didn't believe their experiments anyway. Why is it important? So now we have seen that the simplest way of invoking this coherent behavior in molecule is coming from simple non-resonant scattering. So this tells me that there is a possibility that I can use this to control the way in which my molecular dynamics is going to go, right? So this actually opens up a possibility of such a control. Okay. This also tells me that theorists so far has never thought about this process, and hence when they calculate cross sections, they don't consider this kind of channels where multiple resonances are coherently excited. So again, it's a challenge to them because kind of states that we have seen interfering with the existing negative ion state are also not found by our matrix method. So our matrix method is not only not taking into account such kind of multiple coherent excitation, it is also not getting those antisymmetric states which actually we have found. So it is telling us that the modeling is not yet up to the mark and we are not there, quite there. And as Gagan pointed out, the contrast of interference depends on the phase as well as the amplitude, and that's what happens between the two. Okay. But then the question comes, my both states which I am exciting, be it dipolar dissociation or be it dissociative attachment, they are resonances, they are short-lived states. An individual state has its own lifetime. What is the meaning of lifetime of a coherent superposition of two states of two different lifetimes? How does such a coherent superposition decay? Okay. Now this is a paper in 2001 where Moshe Shapiro showed that if the two states have very nearby lifetimes, then the decay actually beats between the two. Okay. So that means the decay happens, but not an exponential decay. It happens like a beat. So there will be no decay and then suddenly there will be decay and then there will be no decay and then suddenly decay. That's what will happen. But if this is the case, what will happen if my two resonances have far apart lifetimes? Will my long-lived resonance influence the short-lived resonance? Will my short-lived resonance influence the long-lived resonance? We are already seeing effect of this in another experiment, which I will not talk about, where we don't expect a resonance, a shape resonance to play a role, but we are seeing a signature of shape resonance simply because there is a Feshbach resonance, which is a long-lived, also present at that energy. But that we will come to later. Now, another aspect of dipolar dissociation is that is also a resonance, but it's a neutral resonance of autoionization, right? So the kind of isotope effect that I see in dissociative attachment, I should also see in dipolar dissociation. And we do see H2 and D2 behave differently. Now, this is very important because dipolar dissociation tells me that it is the source of high energy H minus. Very important process. It is a source of 10 eV H minus, which is very important for ignition plasma. They are looking for processes that gives them high energy H minus. High energy means 10 eV, 5 eV, 10 eV. Okay, high energy is not MeV, KeV, but high energy H minus, which can go and hit the gas and give away electron very easily, because that's how the plasma can be, ignited very easily. And this is the process now that is actually giving us this kind of fast H minus. It also shows dipolar dissociation, also shows the isotope effect, which is very, very important from astrophysics point of view or astrochemistry point of view, because this is one of the ways H2 can get destroyed. And the rate of destruction of H2 and D2 are different. Okay. And the corresponding H minus and D minus channel formation cross sections are different. So at the end of it, do we understand low energy electron collision? At least the H2 tell us not yet. Okay. So there are a lot more things to know or to learn or to model. And thank you for your attention.
Okay, that was a very nice talk. Vaibhav, so the floor is open for questions, Sushil.
Thanks. So very illuminating. So coming back to the beat here, you're saying it's the superposition which evolves with a beat, which decays with a beat. But then at some point, the superposition has to break.
Yeah.
Right? Because of the decay.
Correct. So the point is, if for that measurement, so that is a theoretical paper. Okay. Nobody has measured it. If you want to measure it, the way in which you have to measure it, you have to find out the excited state population as a function of time of the superposition. And that you will see that the population will go like this. In fact, Moshe Shapiro also proposes is that you can excite two states by laser, and then knowing this beating frequency, right before the first dip happens, you come up with another laser and mix the phase.
Okay.
And if you can keep doing this, and you can get something called Zeno effect, where you will keep your superposition forever. So that's actually something which in that particular paper Moshe Shapiro talks about. So it is the total state, the survival of the total state. That is what is being shown. So any one of them breaks, decays, the entire state is broken.
Thank you. Very nice. Thank you.
Yeah.
Yeah.
So in optics, this kind of things have been seen where you have two levels which are close spaced with same lifetime. Then basically, if you look at the decay, let's say fluorescence, then the lifetime will decay with these patterns, and this bit frequency is basically the energy difference between the two.
Correct. The only problem is, the only thing is that the question that now we are asking is, so this is true for very close by lifetimes.
Yes.
If the lifetimes are far away, then the beating frequencies also will be. Yeah. Because
No. Lifetime is different from, tau. Yeah.
So, but what we are saying is that we have now another probe, which is a dissociation, which is competing with these lifetimes. And now when the lifetimes are far apart from each other, but are going to contribute to the dissociation, we want to see how does this play a role in dissociation. That's something which we don't know. So, but we are seeing evidence of this in our new experiments with bigger molecules.
There's a question.
Yeah, sorry. So my question is also about this beat between different decay lifetimes. So, so maybe this is, too crude a modeling. So I understand beat as, cosine omega t plus cosine omega plus delta omega t as having some delta omega kind of term. But now, with a decay, it's like a complex frequency, let's say. But if I want to write it as e to the power minus gamma t cosine omega t plus e to the power minus gamma plus delta gamma t times cosine omega t, then I don't get any beat, right? Because it's just some amplitude. It's just an amplitude change, time-dependent amplitude change. So it doesn't look like any beat to me.
No. So okay. So beat is not in a true sense of beat.
Okay.
In the sense, it is not when you have two frequencies matching and
then there's a delta omega.
Then the amplitude varies like this. It's not like that.
Okay.
But the decay is happening, will happen within those two decay curve. It cannot go beyond that. That's what it says.
Okay. I got it.
That's
okay.
Yeah. Okay. And the way in which it happens is you have a spurt of decay, then there is no decay, then there is n spurt of decay and no decay, and that's how the system actually decays. This is what the theoretical model tells us. And that's what people have also observed in the light emission from excited states, for example, if you have two states very nearby.
Okay. Thank you.
Yeah, I was curious about the experimental part. So you have many processes which are happening. So how cleanly you can select a particular process? That was and also the other thing is that I felt this inelastic process will be very rare, isn't it, in terms of cross section?
So the answer to the first question is, in order to select this, we look at negative ion, because if you look at all those processes, the negative ion product is only from 2. Right? And then they are very well defined for energy. So if I know the energy,
select a particular energy of the bombarding electron,
and I look at only negative ion.
And see what is that energy.
So for dipolar dissociation, any energy above 17 eV, and I should see this.
But
and that's the point. Any energy above 17 eV, the only process that gives me H minus is dipolar dissociation. There is no other process that gives you H minus. That is why we have gone for negative ion. We can see this in positive ion also, but it will get masked by the ionization.
But if you have an electron of say 20 eV or so, I mean, it's losing so much of energy. I mean, the process would be very rare, I guess.
Okay.
So
now the cross section. So if you look at the cross section, it is 2 to 3 orders of magnitude lower than the ionization cross section, but it is not negligible. It is of the order of 10 power 19 to 10 power 20 centimeters square, whereas typical at that energy, the typical ionization cross section are 10 power 16, 10 power minus 16 to minus 17 centimeters.
So if you have a dissociation of a particular molecule, I would expect that it would look symmetric. I mean,
yes.
So what is your explanation why it is so?
Yeah, so that's precisely the point, is that if that dissociation happens from one state, it should be symmetric. It is happening from the coherent superposition of 2 states of opposite parity, and that's why it is breaking this inversion symmetry. That's the whole.
Can I ask a question here?
Yeah.
So I sort of am trying to understand, these are all the incoherent sources that you are using. So suppose now you have a control and you have a specific coherent source. What experimentally would you observe? Would you sort of enhance these coherences, or you would actually make the coherence?
So I can play with the coherence, and then if I have hypothetically, if I have a fine tune, I mean, if I can tune the phase between the different partial waves.
Yes.
Or you can start with bezel kind of beams, or different beams with well-defined phase between different partial waves.
Phase locking of all
I
these
can play with whether I get H minus in backward direction or forward direction or equal on both. That's what.
So that's what I'm saying. So you will enhance the asymmetry quite a bit.
Yes.
So have you tried? But you're thinking of doing that, or it's hard to do those?
It's not trivial to get that kind of electron. That's the problem.
But that would be exciting.
Yeah. But what tells us? In fact, our D2 measurements are telling us that the electron energy also can act as a parameter, because as the energy changes, your phase changes. So you can act that as a parameter and vary the asymmetry.
Yeah. How do you know your DEA cross section is same for any kind of molecular orientation? Because if the cross section is not same, then you may see that kind of asymmetry in your image.
That's correct. So cross section is not same for all orientation. Of course, not same, and that's because the cross section depends on angular momentum transfer, and all the angular momenta do not have equal probability for all orientation. So the cross section is not same. However, if the system has intrinsic inversion symmetry, then the cross section should have inversion symmetry. That is given. Okay, because once the electron is attached, the number of times electron is going to evolve within that H2 minus is much faster compared to H2 dissociation. So the time it is going to take to rearrange itself is going to be so short that the memory of where the electron has come from is lost. Now, if you have this H2 minus, the H2 minus is also inversion symmetry. So the dissociation should show inversion symmetry. You can think this is a very classical way of looking at it, but this is if that makes you understand.
Also, just last question. can this effect be looked at in another experiment where I think you mentioned about the electron coming out?
Yes. So this particular.
So this is, you followed the molecular angular dynamics, the molecule fragments and the.
So it's the same signature. So I didn't show that. But for example, dissociative attachment, you have a negative ion formation. So if your dissociation channel is showing you
Right.
this coherence,
Right.
in principle, you should also see this coherence in electron ejection channel.
Right.
Yeah. Now that there is also a funny story. People looked at electron ejection, resonant electron ejection at 14 eV from H2, and they see forward-backward asymmetry.
But that was not interpreted like this.
They blamed
at
their
this
experiment.
point. Okay.
Seriously, they blamed it. They said this might be our problem of acceptance in different angles, so it may not be the.
But it was published.
It was published. Yeah, but then if you do systematics and actually cross-check your experimental setup, in principle, you should be able to answer that question. I mean, answer that point. They didn't do that. They just brushed it aside, saying that it is a problem of. But that later on, it was consistently. I mean, it doesn't make sense that all over the world people are doing experiment and seeing the same kind of problem. So there is something more than just an instrument.
Reference story
is a new
acceptable.
Yes,
because you are dealing with hydrogen atoms with something like that.
Yeah. So that's what I mean. That is the only explanation that can explain
I
this.
understand the explanation is okay, but I mean.
Now the point is, so that is what is the question: is that can theoretician come up with a model with either proves or disproves what we are saying, what is our model is? Because experimental fact is fact. We cannot change that. We have a model to explain it.
Yes, there is a model.
This is what I'm saying is a model. I don't have any evidence other than the experiment for that. Now the theoretician has to come up with the explanation.
Okay. Well, Kajuriti, do you have a question? Okay. Let's thank Vaibhav for a fantastic colloquium. Profound questions were raised. This is how it should be ending at, and let's have more discussion on it over, cup of coffee. Thank you. Thank you all for coming.